Lesson 2.2 goes over some of the introductory content with regards to inverse, and the objectives that we're going to cover specifically today are listed there in bullet form. So if you can pause the video and read those and then come back to me. Okay, so what exactly is an inverse of a function, and how can we justify that two functions are inverses? These are several of the questions that we are going to answer today. But let's jump in first and look at these tables that are displayed here in example 1 and example 2. Looking at example 1, they're giving us 4 points that are sitting on the f of x function. Now we don't know what that f of x function looks like, but these are the coordinates. So what I want you to understand about inverses is if I asked you to find the inverse of this given function f of x, you are merely going to need to interchange the x's and the y's. You are only going to swap these values. So it is as easy as making the x's in this table become the y values. So I'm going to write -4, -3, 0, and 3. And the y values will become the x's, 19, 15, 3, and 15. Okay, now I'll explain to you why this interchange is happening. But for now, as far as the method of approach, all you will do is interchange the x and y. So if you need to write this down, you will only need to interchange the x and the y coordinates. All right. Now, if you would take a second, look at this here, the f of x function. Is that, I should say, the f of x relation, is that table a relation that displays function values or not? Well, if we look at the x values, we'll notice that none of these repeat, so this is a function. Okay. Now, how about the inverse? How about this inverse table? Is it a function? Your answer would have been a no. And why is that? Well, we would notice that the 15 in the x values are repeating. So no, the inverse is not a function. Go ahead and do number 2, pause the video, and come back and check. Okay, so if you looked at this table, this is what you should have done. And the inverse is indeed a function because none of these values right here repeat. Okay, when it comes to relations given in a list format as seen in problems 3 and number 4, nothing is going to change with regards to this. Defining the inverse, you are just going to still create one of these little braces. Let me do this again. And in each set of parenthesis pairs, you are going to just flip those two numbers. Okay, interchange that x and that y. And then just close off the list. All right. And again, checking to see if this inverse is a function. You are merely looking at those x values, and as you can see, it is going to be a function because none of those x values repeat. All right. And I'll let you go ahead and do number 4 on your own. Pause the video, come back and check. Okay, go ahead and look, and number 4, the inverse fails to be a function. There's repetition in the x. Okay, moving on. So down here at the bottom of the page on number 5, I have 6 graphs displayed, okay? Each graph has an equation, y equals x plus 2, 3x squared minus 7, and so forth. So right now, what I want you to do is look at these 6 graphs, and I want you to determine if the graph you are seeing is a function or not a function. So go ahead, and I want you to tell me, yes, it is a function, or no, it's not a function. Okay, so let's see what you did. So you would have, if you used the vertical line test, you would have told me that every single one of these is a function, because if I were to draw a vertical line test on any of these graphs, it would have touched only one time, right? One time. Anywhere that I drew this vertical line on these graphs, every single time, as you can see me drawing, every single time it touched one time, anywhere on your graph. So I'm just randomly putting this ruler anywhere, and every single time it touched one time, anytime I drew the vertical line test, okay? So, whoops, I meant to erase. So every single one of these graphs are a function, all right? Now what I'm asking you now is, I shouldn't say are, let me phrase it, I'm trying to look for a different way. For each of these, each one, the question I want to know is the inverse of the sketched graph a function? So this is my question to you. You already just told me that the graph you are looking at, all these 6 are functions. But what I want to know is the inverse of your graph a function. So you are possibly looking at this and you're like, well, you only gave me the graph of y. You didn't give me the graph of y inverse for each one of these. So I can't use the vertical line test to determine whether or not the inverse of these graphs are functions. So there's a thing that you can use. It's called the horizontal line test. Okay. And if you use the horizontal line test, that will help you determine if the graph inverse is a function. And you don't have to have a picture of the graph of the inverse to determine it. So all you have to do is this. 1-to-1 means the following. The first word 1 means that it passed the vertical line test. Why? Because your line that you drew vertically passed one time. So I'm going to use a red here to show that this one right now passed only one time. Okay, so this function, the blue is this graph, the blue graph is a function. Is the inverse a function? So what we're going to do, I'm going to use purple, or let's use a light blue, or not a light blue, actually. Let's use orange. Let's draw a horizontal line test anywhere. So I'm going to draw a horizontal line, and I want you to see that the horizontal line only touches one time. So if the horizontal line test also passes, what you are telling me is that the graph is 1-to-1. And 1-to-1 is just a synonym for invertible, which means that the inverse graph, which we have no idea what it looks like, is a function. So if it passes the one-to-one test, by passing the vertical and the horizontal line test, we know that the inverse graph is a function. So drawing a horizontal line on this one, let me make this a little bit thicker here. This graph here, it failed, right? So that one does not have an inverse that's a function. So this one is one-to-one. Let me circle the ones that it is. How about this one? This one fails to be one-to-one. It passed vertically. Let's do the vertical one. Okay, it passed vertically, touched one time, but it failed horizontally. Vertically, it touched one time. Horizontally, it touched 1, 2, 3, 4. Remember, I only want it to touch 1 and then 1. So that one definitely doesn't work. Does this one work horizontally? It did. It touched one time. How about this one? It did. One time. How about this? Yes, one time. So this one, and this one, in addition to the first one that I circled, all have inverses that are functions. Okay? So please recognize, though, when you use the horizontal line test, it has to pass the vertical line test first. Okay? So if it fails to be a function in the first place, if you don't get a one intersection using the vertical line test, there's no need to even continue with the problem. Okay? So an example of that would look like this. Let me just draw a graph down here. Let's say I gave you, here's the y-axis and the x-axis, and I gave you a function that looks like this, right? Something like that. And you go and test the vertical line test. So here's your vertical line test, VLT, and it touches more than once. So the VLT fails, and so you stop. Okay, it's not a function. So you don't even test for one-to-one, because one-to-one means it has to pass the first time. It has to pass the first time, okay? All right, so vertical line test if a graph is a function. Horizontal line test to see if the graph's inverse is a function. Moving on. So over here, I'm only going to do like maybe just one problem here or two. But I wanted to show you guys, specifically graphing wise, why we switch X's and Y's on the table. Here's why. Whenever you guys are going to sketch the inverse graph of a given relation or a function or whatever, what you're going to do is reflect it over the y equals x line. Okay, I'm going to specifically do number 7 because this one is easy for y'all to see how the reflection works. So first, let's draw the y equals x line. Okay, the y equals x line is going to have a slope of 1, right? Because y equals x, mx plus b, right? Let me write it down here so you can see what I'm talking about. Y equals x in comparison to y equals mx plus b means that your m is going to be an invisible 1 and your b is a 0, right? Here's your 1x plus 0, right? So y equals x has a y-intercept of 0, and then it goes up 1 over 1. So here's 0, up 1 over 1, up 1 over 1, up 1 over 1. So that's why I have this ruler right here. And what I'm going to do, I need to put it here at a 45. degree angle. And we're going to draw this line, if I can actually draw it without shifting this ruler. Oh my goodness gracious, what's going on here? Okay, here we go. So here's that y equals x line. And what it's telling us to do is the following, okay? Each one of those points on that graph are going to be imprinted on the other side of the y equals x axis. So if I were to fold this paper, so to speak, this graph is going to end up on this side, and it's going to imprint itself on that side if I bent it on that dashed line. And so we're going to figure out where that goes, okay? So let's figure this out. So in this dot right here is a 2. Wow, that's a little bit too thick. So let's make that a little less thick there. This here is 2, -2, this dot. So we're going to flip-flop and we're going to go -2, +2. And then this one over here is 1, 2, 3, 4, 5, 6, 7, 8, -2. So now we're going to go -2, 8. 1, 2, 3, 4, 5, 6, 7, 8. So if I can actually write it. All right, there's the -2, 8. And then we have 2, 1, 2, 3, 4, 5, 6. So 2, -6. So we graphed -6, 2. And then the last is going to be 8, -6. So we'll go -6, 8. So here is, let's connect the dots here. That is the imprint of the black graph towards the green. So if I were naming the black graph some name, let's call it M, let's call it M of X. This graph would be M inverse of X. All right. Now the black graph is not a function or anything like that, but I'm just trying to get you guys to understand that inverses are just a reflection over the x-axis. I mean, over the y equals x line. Okay. So I want you to remember that specific thing because I am going to ask you guys on the test. Moving on. Finding the inverse given an equation. So let's specifically do, I don't know, let's do number 12, I guess. All right. And then you guys can practice with the other two. When it comes to finding the inverse of an equation, the first step that I want you to make sure you do is I want you to replace your function notation with a y. And then once you do that, I want you to interchange your x and your y. So notice how I replace the f of x with a y. And then step number 2, I'm going to switch that x and y. The y now becomes an x. And the x becomes a y. Okay. Now some students ask, can I just go ahead and just do both of those steps in one shot? Absolutely. So what I mean by that is Some students just skip this altogether. They recognize that the function notation is a y and that they go ahead and just change it to an x immediately. So that's totally up to you. Now, third step. The third step is I need you to now solve for y. Okay, so in this particular part, the y is right here, and I need this y to be all by itself on that side of the equal sign. Okay, so here's my equal sign. That means I need to get rid of this, and I need to get rid of this, and I need to get rid of this to get that y all isolated. So what do I need to move first? Well, I'm going to move that -3 first. So I need to add 3 on both sides. Okay, and so when I add 3, x plus 3 are not like terms, so I'm going to keep them separated, and then I have -5y to the second power. Then between the -5 and the 2, I will get rid of the -5 next. -5 is multiplying, so I need to divide by -5 on the right side and divide by -5 on the left. That causes this to reduce to a 1. -5 divided by -5 is a 1. So now, let's move over here to this side. I have x plus 3 over -5 is equal to y squared. So all I need to do is get rid of that squared. So I am going to take the square root of y squared. Therefore, I must do it on this side as well. And that square root will undo with this square, leaving my y isolated, and my final answer can't be reduced any further. But since I square rooted both sides, I must put a plus minus in front of my final answer. So now that I have arrived to solving for y, step 4 is going to require us to just rewrite it in function inverse notation. So go back, revert back to how your problem was given. I was given f of x. I found y, which really is my f inverse of x. And just write down the quantity that you found y equal to. And then this is the inverse of the graph that was given to us. These steps will not change. These steps to find the inverse will always be these. Okay? Last but not least, let's go down to the bottom. Let's see. It doesn't really matter which one. I guess we'll do number 14. Okay? Now, let me read the directions first. So here in number 14, what's going to happen is, unlike the previous problem where I asked you to find an inverse, I'm actually giving you what the inverse is. So if you look at number 14, I'm giving you f of x, and I'm giving you the answer to the inverse of f of x. Okay? So I'm doing the work. But what I'm asking you to do is verify, in other words, double check me, and prove to me that I indeed did find the correct inverse, okay? And so to be able to verify, you are going to have to do the following equation right here. You are going to take the composition in both directions. So I need to say composition in both directions. Okay, so you're going to take one function, dump it into the other, and then vice versa. All right, let's make that look like a M and a P. Okay, so let's show you how this exactly looks like. So let's stretch over here. We're going to go do f of f inverse first. Okay, we're going to do this piece here first. Oh, and by the way, I did forget to mention, notice that both times when you do it, your answer has to be x. Why? Why does it have to be x? Because inverse is the reflection over the y equals x line, right? This is why it has to be x. It has to be a reflection over y equals x. Okay, so let me go back here, sorry. Okay, we're back. So let's do the first one. We're going to take the first function. The first function, we're calling it f. Wrong pen. We're calling it f. And I'm going to substitute the other function. The other function is 5x minus 11. That's what I'm going to substitute. So I'm looking at this function f. That's why I called it f. And I'm going over to the other side, grabbing this stuff and putting it in my parentheses, okay? So let us do the math. So every x in f, I've got to replace with 5x minus 11. This is the stuff I'm going to substitute with. So I need to look at my f function, and I need to substitute the x with 5x minus 11. Here we go. So notice this x was replaced with this new x. So instead of x plus 11 over 5, it's 5x minus 11 over 5. So now let's simplify. Notice this negative 11 and positive 11 is going to zero out, leaving us with 5x over 5, which reduces to x. And that's exactly what we want based on our definition for verifying. So now I'm going to do it in the reverse. Okay. So instead of starting with the f function, we're going to start with the f inverse function. And we are going to substitute. See, we're starting over here with f inverse, so we're going to substitute the other one. X plus 11 over 5. So now, let me erase this here. So what I want you to notice is, now if you're looking at this inverse function, I am going to get rid of this x and replace it with x plus 11 over 5. So instead of 5x, it's going to be 5. Replace the x with this minus 11. So now start cleaning up. What can you clean up? This 5 divided by 5 makes a 1. So I'm left with x plus 11 minus 11. This plus 11 zeroes out with that 11. And so we're equal to x. And once again, as long as I get an x on both compositions, I have verified that those two functions are inverses.